Okay, so can you see my screen?
Yeah.
All right, so today we will be moving on with the next lectures. So the general perspective on graph neural networks and some application stuff like how it is trained, how to do augmentations, and so on. There are many slides, so we will be rushing through them, not to spend that much time on that. So first of all, as we have seen previously, the graph neural networks are composed like layers. So we have a graph, we pass it through a graph convolution, then apply some nonlinearities or other regularization stuff, and then stack another layer on top of that. And we also saw that we can see the computation graphs as follows. So for a given node, we go through its neighbors, through its k-hop neighbors, and then pass messages along the neighbor edges to that node and aggregate those messages. All right, and everything, the basic concept in graph neural networks is that you have two stages, so a message stage and an aggregation stage. And we will look at them in the most popular architectures, so GCNs, GraphSage, and Graph Attention Networks. And we will also look at how to stack those layers. Okay, so a single layer, as I said, composes of a message passing and aggregation. What you want to do is use the messages that you get from the neighbors and then aggregate them into a node embedding, but the aggregation should happen in a way that is permutation invariant, so the ordering of the nodes shouldn't matter. And for example, how to compute the message. You take the representation of the node from the previous layer or the original node attributes if you're at the first layer. Then you compute the message for that node. And how can you do that? You can apply some deep neural networks, but you can also just go with a single linear layer, so linear transformation. And then for the aggregation step, you take the messages from all neighbors of a node and aggregate them permutationally invariant. So for example, for the basic cases, you can just compute the sum, mean, or max over these messages. But there's a slight problem. First of all, if you do such an aggregation, then you're only aggregating over the neighbors, but you do not consider the message or the features of a given node. So what you need to do is also to use the representation of that node, for example, transform it using another transformation matrix, and then concatenate both features, so the new node features and the aggregation of the neighbors. Yeah, again, you compute messages, you aggregate them, and then you can also apply some nonlinearities on top of that. And for example, in the most popular, I think, architectures of the graph convolutional network, what you do is actually you sum over the neighbors, over the neighbor messages, renormalize them over the node degrees, and then transform them using some weight matrix. But you can also move that matrix inside the sum, and then this part stands for the message, and the sum is just the aggregation function. Also written like this, it's not really matching the GCN implementation because they use asymmetrical normalization instead of just dividing by the node degree. And then you only sum over the messages. So this is just a decomposition right here. In GraphSage, you do this slightly different. So first of all, you take a general aggregation function, which we will go through in a second, aggregate the messages, then concatenate them with the features of the given node, and then transform it, apply some nonlinearity to that. So the aggregation is in two stages, over the neighbors, and then concatenate it with the current features. And what can you do for the aggregation? The authors of GraphSage checked various ways. So for example, just take the mean, so like previously, or do some pooling where you first transform either with a single linear layer or with an MLP the representations and then take a mean or a max, or you could do multiple passes through an LSTM with reshuffled neighbors, because like LSTM introduces some ordering and we do not really want ordering of the neighbors. Another thing in GraphSage was that they...
I had a question here, if you mind going back one slide. Yeah. So on the LSTM, right, it's, I think one of the requirement is that the aggregation function is permutation invariant, right?
Yeah, exactly.
So when you have LSTM, is it strictly we are, passing a few of the reshuffle nodes or all of the reshuffle nodes?
Theoretically, they write in the paper that you should look through all the combinations of the neighbors, so or the permutations of these sequences. But in real world applications, it's infeasible. You cannot do that. Even for smaller toy examples, it's too expensive. So they just propose to use like, I don't know, 5 or 6 different shufflings, and that is enough for the LSTM approach to work.
Okay. Thank you.
Yeah, no problem. Okay, the next thing was the L2 normalization. So they apply it so that each representation will have it will be a vector of unit length. And this, they show that also this improves the results. And the last architecture we want to talk about are graph attention networks, where the authors saw that if you do such a aggregation and message passing, then, for example, in GCN and GraphSage, what you do for this weights, how you combine the messages, is that you assign a constant factor or a deterministic factor right here. So only the inverse of the node degree. And in such case, all neighbors are equally important for that node, but we do not really want that. We want to generate this aggregation weights, or here called attention weights, to be learned from the graph data. And how we can do that, we say, okay, we take the representation of a node U, we take the representation of a node V, then we can also transform them, and then we pass them to a attention function, which computes attention scores. Then these attention scores, we renormalize them, for example, using softmax, so that they sum up to 1. And then we substitute them back into the original equation. And how can we compute this attention score? We can simply take the transformations of the node representations, concatenate them, and then pass them from a single linear layer. And that is everything we need to do. But for...
I have a question here. Sorry. Would you mind going back a couple of more slides here?
This one or previous?
Yeah, one more. Yeah, I think the first where he introduces the one more. Yeah, right here. So in that first equation, right, I think that attention weights, what we understand is you are trying to compute a weighted combination of your input features, HU. Can't we observe the alphas inside the W matrix? Because that essentially is also doing the same thing, right?
Perhaps we can do that, but I didn't really think about this in this way.
Because it's a, if you take one neighbor V or U, right, which is a neighbor of V, it's a constant weight, right? So I can multiply, you know, the row, corresponding row by that number, and it becomes a different W. So I'm just wondering, shouldn't W already be doing that?
I don't think so. Why? I think maybe it's because W is also shared. So wherever you multiply by the neighborhood, it's gonna be the same. So here the thing is that you are learning at the same time a different weight for each one of the neighborhood. So that one
okay,
it should
okay.
be
W is,
yeah. So
yeah,
it
W
will,
is
it will,
basically invariant, you know, across all the entire graph.
yeah.
But here, the alpha basically takes care of the individual importance. Okay,
Yeah.
okay,
So it will be like a filter for each pass, for each neighborhood.
okay,
Yeah,
okay.
also another thing is that this attention weights do not need to be symmetrical. So if you have, for example, the attention weight from node U to V, it can be far greater than from V to U. And that's also
Okay.
another thing.
Okay, so okay, I see. So W is more of, I think it captures the, what I would say, the global structure, and alpha, the attention basically captures the local structure. Is that how I should think of them?
Hmm.
No, because it's not a structure. Like W, you cannot think of like as an adjacency matrix. W is just the how you transform features from the this not U to W. That's how you get only features for not U. So it's not basically like a structure of the graph. So it's basically how you do the representation learning part. So for this representation learning, you want to have like a low pass filter. So where you want to amplify features that are more important for this neighborhood or this task, in the sense that W alpha is learned. So this all is part, you can think of as part of the representation learning part. But it's not the
Sorry, maybe
structure.
I was maybe I put it in the wrong way. I was thinking of W as more as that it captures the structural component of the graph, and alpha captures the interaction, you know, node to node specific interaction.
Yeah, it's still, yes, but it's still like the structure I think is not clear. But I'd say like it's more like filters. So you can say like U is basically the structure of the graph or anything. So basically it like W can be like a global filter. Like if you put it like an alpha is gonna be like a low pass filter. And that's basically like, there are many ways of doing like attention. So this is just a soft attention where you want to pass like some information between U and B. So yes, I think, but I think just a structure is just for me at least it sounds a little bit confusing.
Would you mind explaining what you say by low pass filter?
Okay, low pass filter is like in convolutions, when you have convolutions, when you have only the, in this case like alpha is gonna have, is basically just a weighted sum here, because you are weighting over the neighborhood.
Right.
So you're just allowing like information that has, in this case, alpha, when it's higher, you're gonna pass more information. When it's lower, you're gonna pass less information. So that's how you rank what is important or what is less important for this node. So basically that's what I mean, like for a lower pass filter, where you allow like the information that is important to pass.
Okay,
And
I was
when you,
thinking low pass means, you know, are you thinking of a signal processing perspective, like low frequency?
Yeah.
But if you
And
have low frequency, you have to capture larger distance, right?
yeah, it's the opposite.
But here you are just looking at only the nearest neighbors. So it's probably high frequency.
Let me think.
Sorry, maybe it's a little bit off the topic. I was just trying to.
Yeah, but that part is interesting because you can align this also with signal processing. But yeah, I think we'll get that in other lectures. But I think I'll write that also, because I always think that as a low pass filter. But I think you're right.
Yeah,
but
I was
also
think that it would be high pass, right? Because you are capturing the features at the change at very short length scales, right? In physical length scales, that means in the frequency domain it would be high pass.
yeah, but okay, I'll get back to you in that. But I think yeah, I don't have an answer to that. But I still think it's low pass. But
Okay,
I don't know how to justify.
okay. Thank you.
All right, so let's move on. Okay, and basically, if you would use a single attention score, practice shows that it's quite hard to run that. So it converges hardly and there are many problems. Also in other domains, people came up with the idea of multi-headed attention. So you just compute multiple attention scores and then, for example, aggregate them or concatenate the outputs of such aggregations. And that should really improve your training quality. Okay, so, yeah, there was also an example how it looks in the Cora citation network, and that using this graph attention, you can gain 1.8% better scores. Okay, but in practice, if you dealing with any kind of deep learning, you also use other techniques. And also you could view these GNN layers as just neural network layers. So you could also combine them with batch normalization, dropouts, some activation functions, or other attention mechanisms. And yeah, for example, batch normalization should stabilize the training, dropout should prevent overfitting, attention gating should control the importance of the messages, as we saw. And you could use everything that was developed in other deep learning areas here, and it will be still fine. So just a quick recap, batch normalization takes a batch of examples, batch of nodes, for example, and computes the mean and standard deviation, renormalizes the embeddings of the nodes, and then also additionally transforms them using some training loop parameters. Dropout just deactivates some neuron in the forward passes with a random probability p. Okay, for activations, this is something you should probably know, so I will skip that. And yeah, that's everything for this. Let's move on. So how can we stack GNN layers? First of all, we can stack them just in the standard way, so sequentially. But there's a problem with oversmoothing, and how does it, what is actually oversmoothing, that all the embeddings of the nodes became essentially the same embedding. So we cannot differentiate between different nodes. And why that happens is with every additional GNN layer, we increase the receptive field. So the k-hop neighborhood we can see with this graph neural net. And for example, in this example, where we have two nodes, for example, with only one hop neighborhood, we have one shared node. With two hop neighborhoods, it's even more. And with three hop neighborhoods of 3 GNN layers, we cover up essentially the whole graph. So the two representations will be nearly the same. And this is something we want to avoid. And how can we do that? First of all, we should not just add additional layers and hope that our network will train better. We should just try to add them sequentially and look how the performance goes up or down. Also, we can use more expressive GNN layers. So for example, instead of using just some linear transformations, we can use, for example, MLPs in the transformation aggregation stages. We could also combine GNNs with non-GNN layers, so like MLP layers for pre-processing and post-processing. We can add skip connections, which are also fairly known from, for example, in computer vision. Okay, and what else? Okay, so another thing we can do is we do not necessarily need to pass the graph that we have exactly as it is through the GNN, but we can also augment, for example, the features or manipulate the graph structure. And why should we do that? For example, we can have a graph where there are no features, so we need to come up with some features because graph neural networks need features to work with. In terms of the structure, a graph can be too sparse, so we would need to perform multiple rounds of message passing. If the graph is too dense, then the message passing becomes too costly. And if the graph is too large, then good luck, we cannot fit it on any kind of GPU, so we cannot train it. Okay, so what are the solutions for all these problems? If there are no features, we just need to augment some features. If the graph is too sparse, we can add virtual nodes or virtual edges. If it's too dense, we can perform neighborhood sampling. And if the graph is too large, we can subsample subgraphs and compute embeddings for those subgraphs. And regarding the first feature augmentation, so what can we do? For example, if we do not have any node features, we can just assign constant values to all nodes. Or we can assign a unique ID to every node, for example, as a one-hot vector. And what are the pros and cons for both of these approaches? In this case of a constant node feature, the expressive power is not that great, but it is possible to perform inductive learning, so to generalize for unseen examples. The computational cost is also low. On the other hand, for this one-hot node features or these node IDs, the expressive power is much higher, but we cannot do inductive learning because, like, if another node appears, we would need to extend the one-hot encoding, and then we would need to retrain the GNN from scratch, which is missing the actual point. Also, the computational cost is high because the features are in the range of linear to the number of nodes. Okay, also another thing is that feature augmentation can help to overcome the basic restrictions on graph neural networks, because, like, for example, in these two examples, if we consider node V1, then we cannot distinguish that it resides in a cycle of length 3 or 4. Its neighborhoods are exactly the same, degree 2 neighbors, and we cannot distinguish such cases. But if we, for example, add some additional features or just bootstrap such features that we have the number of cycles of length 0, of length 1, 2, 3, and so on, then we can distinguish these two cases. Other solutions that we can do, we discussed that already in lecture 2, so we can compute, for example, the clustering coefficient, the page rank centrality, or other centrality measures. Okay, moving on to structure augmentations or general structure manipulation of a graph. If graphs are too sparse, we can add virtual edges. So, for example, we can add connections to 2-hop neighbors just by adding the squared adjacency matrix. This is also something we discussed previously, that if you take the adjacency matrix to the kth power, then we have all the connections to k-hop neighborhood. We can also add virtual nodes. So a node that is connected either to all nodes or just to a selected subsample of the nodes. Then we can assume that message passing is more efficient between those nodes because they have only, they are connected via 2-hop neighborhood. And for the example that was discussed in this lecture was, for example, if we have 2 nodes that are 10 hops apart, then we would need to stack 10 layers just to go through the 10 hops. But as we see with oversmoothing, it's not possible. So we can just add a virtual node and then they are at distance 2. And in general, it should improve the message passing in sparse graphs. Neighborhood sampling is quite intuitive. We do not process messages from all neighbors, just from a subsample of the neighbors. For example, if we have like a node that has 10 millions of neighbors, then computing such message passing would be quite costly. So we can just, for example, subsample every time randomly 10 neighbors and do multiple training iterations. And yeah, that is everything for this lecture. Do you have any questions for that lecture? Okay, if not, then we will move on to the second one. There's, I think, a bit of repetition in this PDF file. So yeah, that's something we also looked at. That was done, that was done. Okay, so now we will move on to the training objective, so the learning objective. So what we covered up to this point is that we have some input graph, we have a graph neural network that can produce node embeddings, and now we want to use those node embeddings and also train the graph neural network. So first of all, we will consider prediction heads, so how to use those node embeddings for node, edge, and graph level tasks. For node level tasks, it's actually quite easy because we already have node embeddings. So the only thing we want to do is, given a d-dimensional node embedding, if we have, for example, a multi-class classification problem or a k-target regression problem, then we want to transform those features using some matrix to get it to the k-dimensional vector. And then we can combine it with some loss function, and that's everything. For edge level tasks, we need to combine the node embeddings of nodes that are connected to a particular edge. So we can either do that like in the case of attention, so just concatenate the 2 node embeddings and then pass them through some linear layer. And again, we can choose that linear layer in such a way that it outputs a k-dimensional vector, so we have k targets for either prediction or regression. We can also use the dot product of the corresponding node embeddings, but in this case, we will have only one value for that edge. So if we want to apply it to a k-way prediction, then we need to do something similar like in the multi-head attention. So instead of computing the product like this, we also use some additional matrices just to get some different values. And then we concatenate them to get a k-dimensional vector. In graph level tasks, what we do is essentially we want to aggregate all node embeddings to a single general graph embedding. It's just like the aggregation in a GNN layer. So what we can do is just do global min, max, or sum pooling. So either take the min, max, or the sum over all node embeddings. But this is problematic in some cases. So what we can do is aggregate the embeddings in a hierarchical way. And for example, the div pool architecture does it in such a way that we have two GNNs. One computes the node embeddings and the other one computes clusters where each node should belong to. And then we aggregate them in each cluster and then do another round and do it as long as we get a single embedding for the whole graph. Okay. And now moving on to the actual training objectives. So we have some predictions now, and we have, for example, some labels. So
would you mind going back to the previous one? Sorry, where you had the clustering. So this is what you're saying is we do the message passing through, like, using any GNN architecture. And at each round, we have an update of the embedding. And then we use that to, use any clustering algorithm to create clusters.
Not
update
really
the cluster.
Any, but you use another GNN for that. I did not read that paper, so I cannot assure everything, but as I understood,
that one also has to be a GNN, the clustering one. I was thinking, the standard clustering.
It should be possible. That's true, but yeah, in this paper they decided to use another GNN to assign the clusters.
Okay.
All right. Okay, so you can train a GNN, let's say, in two ways, either in a supervised setting or an unsupervised setting. So in the supervised setting, you just compare the predictions to the labels itself. And in the unsupervised setting, you just produce the embeddings, but independently of any particular downstream tasks. Another name for unsupervised that is currently used is self-supervised, but they are often used interchangeably. So in supervised settings, it's quite straightforward. So if you have node level predictions and you need labels for all nodes, then you just compare those, for example, using a cross entropy loss or any other loss that you need in a particular problem. For edges, it's exactly the same. You have some labels for the edges or for whole graphs. But in the unsupervised case, you do not have any labels. So what you do, for example, at node level, you can try to predict using the GNN node statistics, so clustering coefficient, page rank, the node degree, for example. In edge level tasks, you do just link prediction, and this is something that will be considered in a second. And for graph level tasks, it's basically the same as in node levels. So for example, you can predict if two graphs are isomorphic. Okay, so for the loss function, you can either do classification or regression. They just consider these two cases. Okay, and yeah, for example, in the classification case, you can use cross entropy loss. In the regression case, you can use the mean squared error or the L2 loss, so-called. And how can you evaluate it? This is basically the same as in any other kind of problem, not specifically to graphs. So I will skip that. You can use the basic metrics like accuracy, AUC, and so on. So that's basic stuff we should know. Okay. Now it's the tricky part of how do we set up the training.
So
how?
Sorry, I had another question. So regarding the training, I was thinking, when we have, the standard neural network architectures, it's a single, acyclic graph, right? Where, you pass the gradient information. But for graph neural network, should we view this like, how is it done? Is it like, if, for example, if you have n nodes, there are n different DAGs? Is that how? And for each layer, basically, you have the same acyclic graphs, but with different update values. Is that how it is done?
So you mean like the computational graphs, right?
Yeah.
Well, so as far as I know, it should be like generated one graph for each node in this case, but I'm not really sure. So maybe Javier, do you know how it's actually implemented?
You mean to? I didn't understand fully the question.
Yeah. So if you have a CNN, for example, right? The entire network is one single graph, right?
Mhm.
Where you're passing the gradient information. But here, are we basically creating n different graphs, like now, and then within each graph we are basically passing the gradient. And for each,
I think it should be the same. It shouldn't affect because like each node it will be independent of the other ones. So as you carry information of the other nodes, like the computational graph. Oh, you mean that also like some nodes have information of the other nodes, so they share the information of the gradient?
Yeah. So for example, I think he shows, right, if some nodes have, if you have more neighbors, it will be a wide graph. And so when you're actually passing the backpropping the lost data through the nodes, are there n different DAGs that are actually used for backpropping?
Yeah, I think it should be for one. You mean like for one pass, or you mean for one graph? There should be n nodes back when you do backprop. That's what you mean, right?
Yeah, n different backprops. That's what I was thinking.
I don't think so, because I think that would be like super expensive. I think you share the information because the gradient is gonna be the same at the end.
Okay. Because yeah, I mean the values would be the same, the node values, but but the gradients you compute might be different, right?
Yeah, but it's just like how do you traverse that graph? So the different paths you take is just gonna be different for each neighborhood, or for each, at least for each node.
Yeah, just a thought that came to my mind, how it's implemented.
Why I said that, at least because also like in the PyTorch geometric, I don't see anything specific like in terms of the implementation of how to do backprop. So I think since it's using the default PyTorch, I think it shouldn't affect, it should be the same.
Yeah, I think you should be able to use the backprop structure for PyTorch, but there should be like n copies, n different possibly graphs where you are doing the backprop. That's what I was thinking, where n is the number of nodes.
I don't think so. I mean, at the end of the day, it will still be a matrix multiplication, right? And at each L level, you'll have like one representation, and then you do one iteration would be again like one matrix multiplication, and then passing it through an activation layer or something. So I don't think it will be like multiple versions of these. But I haven't gone through PyTorch geometric implementation, but that's what I guess.
Yeah, because as far as I know, like how it works, the differentiation part that is in PyTorch, for the backward, you have a reverse, a forward mode differentiation, right? Where you compute the gradient at every step. So when you do backwards, you don't have to recompute. So everything is calculated. So I think since everything is calculated, independent of which node are you applying to, or which node are you doing backprop, you're not recomputing everything for each node. So it's already computed. So you're just adding up for the path that is already computed.
Okay, thank you.
Yeah, but I might be wrong too.
Yeah, but it's actually a great question. I didn't really also think of that previously.
Yeah, but I think it should be still using like the reverse mode differentiation. So you compute everything like while you are doing the forward pass. Yeah.
Okay, so let's move on. It's the end of this lecture, so we will finish soon. So how do we prepare the training? So how do we split our data set into training, validation, and test sets? First of all, we should note that we can either use one fixed split or use multiple random splits. And in case of graphs, it's more that you should do a multiple random splits, because sometimes for a one fixed split, there is a problem with training leakage. So some of the test parts can be leaked into the training set, and using random splits, you can somehow mitigate that issue. And yeah, also that's something what is special about graphs in other domains where you have independent data points. Doing train test splitting or train validation test splitting is actually quite easy. As we can see here, we just take some sets of the data points, but in graphs, these data points, these nodes are actually connected. So if we train, for example, on nodes 1 and 2, they will also affect the stages, the nodes at the test stage. So for example, 5 is connected to 1 and 2. So that's a problem. So what can we do is we can use two settings, the transductive one and the inductive one. In the transductive setting, we keep the whole graph, but only use certain subsets of the node labels. So during training, we use the whole graph, but only use the labels of the train nodes. So for example, here 1 and 2, during validation of the node labels of 3 and 4, and so on. In the inductive setting, after we choose the training nodes, the validation test nodes, we drop all edges that are between those sets. So there's no leakage between those subgraphs. And in the end, we get multiple graphs. Okay, and yeah, for example, in node classification, if we split the data set like this, then we have independent graphs for training, validation, and test. In graph classification, this train test splitting is actually quite easy and well-defined, because like you have multiple graphs, so you can view them as independent data points, and then just randomly assign some of the graphs into training, some into validation, some into test. So that's quite easy. I think the hardest case is to do link prediction. right here, what you need to do is you need to think about the connections of the edges. So we need to differentiate between edges that are used for message passing and then for evaluation of that stage. So we have message edges, which are used in the forward pass, and supervision edges, which are used for the actual training and the comparison with the loss function and so on. But these supervision edges are not passed into the GNN during the forward passes. So, for example, in this link prediction, we want to use the graph of the message edges, and we then want to predict whether the GNN is able. We want the GNN to predict these supervision edges without seeing them in the first place. In inductive link prediction, yeah, we just create multiple graphs defined by the setting into train, validation, and test sets. And for each one of them, we then do another splitting round, where in the training set, we first select the message edges, then the supervision edges. Again, for the validation set, the same procedure, and for the test set. And we need to remember that supervision edges are not inputted into the GNN. These edges we want to predict. Then we also have transductive link prediction. It's the most popular case. And in this case, we need to only assume that we hold out the edges that are in the validation and test sets. And we use the remaining set of the training edges, but also with holding out the supervision edges. It's quite tricky, but let's look at this example. So we have the original graph, then we use the training edges with the message edges. So these edges 1, 5, 2, 4 are passed into the GNN, and we want to predict edge 3, 4. At the validation time, we use the training message edges, the training supervision edges. We pass them into the GNN, and then we predict the validation edges. So like here, 5 and 4. And at test time, we use all of the previous edges and then just try to predict the test edges. So in this example, 2 and 3. Okay. And this is, I think, everything for these lectures. So any questions on that? Okay, if not, then I don't know if we want to finish for today or we still want to go through a paper because like we run out of time. So what do you think? What do you think?
Let's do it next week. We are out of time as well.
Yeah, I think we can do it next week, but just one thing, just to some of the questions. How do I share my screen? Okay, for the one of the Laplacian, this is still is a low pass filter. Why? Because basically when you have the what's called the Laplacian matrix, so that's how you can represent the graph. So here you can decompose that in the eigenvalues and eigenvectors, and basically here, these eigenvalues basically are ordered. So the 0, they are in a decreasing order. So the first filter, the smaller values, so are the ones that carry the most information. So that's why it's a low pass filter. One thing there. So we're taking only the low frequencies. And about the diff pool, also there was a question how the clustering is done. So basically you train to like here you have, we can go over this paper actually, but
what paper is this, Javier?
And this is diff pool. The other one is they basically prove a theorem that is used for low pass filters. But we can go over this paper once we cover some of the theory in signal processing. I think is one of the lectures. And but there's other papers for deep pool. They only show how is the learning is done. They learn also two matrices, where like the first part is just a regular GNN, but then also they learn a new graph. So basically here, Z is a graph, S is is also computed, but you're also like learning different graphs. So these are assignments, and every time this graph is being reduced. So this can go over and over until you stack these layers, basically. So you are called each of these layers are called. It gives you like a graph that is coarsened, and so basically you're kind of clustering nodes that are close to each other. So that's how they do the clustering part, and it's all about also the learning function that they use and etc. But basically, this is how the clustering is done. Basically, just learning a graph at each step. And that's about deep pool. And we can take a look at this paper also. They propose about like there's this problem of oversmoothing that we saw in lecture 7. So this paper is they also say like, okay, there's more about that. There's also other question that I think this paper is a little bit interesting beyond going on over beyond by only looking at just layers. So I think we can cover that paper too. But basically, I hope that answered all the questions. I think I can finish for today.
Thank you. Would you mind putting these two links?
Oh yeah,
in the
yeah.
chat? I would love to look this up.
Okay, so I think that's everything for today. So thank you for your attention, your participation. Thank you for the questions. And see you next week then. Thank you.
Thanks.
See you guys.